Hello there and welcome back. Well, the time has finally come. I've alluded to it for the past 3 weeks, but we're finally going to talk about color space. And my goal as we're talking about this is to understand the practical application of color space because it can get very confusing and very technical quickly. And the goal is to have a practical understanding of it with a minimal scientific jibber jabber. So let's get started. Now, before we talk about how color space is implemented in Nuke, we first need to understand what exactly color space is for. Well, our goal as VFX artists is to have our work mirror reality. And in order to help achieve that, we should be working in an environment that mirrors reality as closely as possible. That's where the linear color space comes in. But what exactly does that mean? Because Nuke works in a linear color space under the hood. That's what everything is built on in Nuke. Well, a linear color space displays the relative brightness between objects as they exist in the real world. For example, if we had two light bulbs where light bulb A is twice as bright as light bulb B, we would see the following luminance values in a linear color space. A would be 0.8 and B would be 0.4. But if we were reading the footage with a logarithmic color space, and we'll go into detail about exactly what this means later, we would see this value. Light bulb A is at 0.8, but light bulb B is at 0.7. But it's not like one bulb got brighter. They're just being displayed in a color space that isn't one-to-one with the actual intensity of the light. So you may be asking, why does this matter? Well, imagine a note was given to you to double the light intensity of bulb B so that it matches light bulb A. In a linear color space, that's as easy as multiplying light bulb B by 2. But then suddenly in a logarithmic color space, our calculation is not so straightforward. In order to match the brightness of bulb A, we would need to multiply bulb B by 1.14. This strange number is required because our color space does not accurately match the real world. We doubled our brightness with a seemingly random multiplier, and you can imagine how difficult managing exposures would be if we didn't have light bulb A to reference. In this image, you can see how a linear color space properly matches a camera's exposure. As we go from left to right, our camera is halving the amount of light that it's letting into our lens. The black number represents a linear color space, and the green number represents a logarithmic color space. And you can see that as we move from left to right, both the highlights and the darks in our linear color space are perfectly halving. But in the highlights in our logarithmic color space, it's being reduced by 0.057. But in our shadows in our logarithmic color space, the number varies heavily. In the first panel, it's going 0.06 down. In the next one, it's 0.07, and then it's 0.08, and then it's 0.12. And so as you can imagine, this would make it very difficult to just double the brightness in a given area. And imagine that we had multiple different cameras that we're combining footage from. They're all going to have different color space curves. And you could imagine how difficult it would be to get the rolling off of the shadows to look correct between different cameras because their curves are all so different. And that's another one of the reasons we want to convert all of our elements into a linear color space. It brings them all in line with one another so that any changes we make are uniformly applied across our footage. For example, say we wanted to double our brightness. We would just multiply all of our elements by 2. If we didn't convert our elements and they stayed in a logarithmic color space, we would need to figure out that weird multiplier for each of our elements in order to technically double our brightness. And this is also directly related to CG compositing, because 99.99999% of the time, when you receive a CG EXR, it will be done in a linear color space. And unifying that with your footage is very important, and it's going to be so much harder to get our CG to feel real if our comp is not properly set up in linear color. So next I'd like to go over the 3 main types of color spaces. There's linear, logarithmic, and viewer, aka video, color spaces. So as we discussed before, a linear color space imitates real-world brightness values, in that it displays the relative brightness between the objects as they exist in reality. It should be the working space for every compositor using Nuke. If we were to look at an image in its linear form, it's actually a pretty ugly thing to look at. But don't worry, we're just using this to work, and we're not using it for the final viewing of our product. In our graph at the bottom, you can see that on our x-axis we have the real-world brightness, and as it's increasing and doubling, our footage RGB value is also uniformly increasing, giving us a linear color space. And one of the key components of a linear color space is that it's floating point, so we can have values that are brighter than 1. The other color spaces generally can't do that. So now let's talk about the logarithmic color space. So a logarithmic color space, aka a log color space, is used by high-end cameras to retain the most amount of data possible. They do this by compressing the luminance values very tightly, typically between the values of 0.1 to 0.7 if you were to sample it. This makes the relative luminance data not accurate to the real world. When they're recording with these cameras, they're trying to get the most amount of dynamic range in their image as possible, so they're flattening all of these values. And because of these flattened values, a log image will appear very washed out and flat, as we can see here. There are many different types of log color spaces. There's the Alexa V3 log C, there's S log, there's Red Dragon log, there's Canon log. There are slight variations between these color spaces, but they all follow the same basic principle. You compress the luminance values to retain as much detail as possible. Although you can retain large amounts of data while recording to log, thanks to high bit depths in cameras, you are still limited to a range between 0 and 1. Anything beyond these values will get clipped. And that's why the curve is so flat at the top, to retain the brightest brights possible. Now the third type of color space is what I call the viewer or video color space. This is a classification of color space that I've kind of come up with because it's very broad, but ultimately, if your color space isn't in a linear color space or a log color space, it's most likely in a viewer color space. This color space represents footage that has been artistically color corrected. It is not based on real-world values, but rather what looks good to the eye. When a colorist begins working on a log footage, he or she will commonly first apply an sRGB or Rec. 709 LUT to have a baseline color space conversion to make it visually appealing. The LUTs we have added to our shots throughout the weeks follow the exact same principles by making our footage more aesthetically pleasing. You can see visually this image looks the best of all the color spaces we've viewed so far, but its intent is to be viewed, not to be worked on, because this also does not accurately represent the increasing in brightness values. Typically, viewer color spaces will not have that much data in them, they're not floating point, and they're typically the hardest color space to convert to linear because you don't know exactly what the colorist did to them. In Nuke, we're working in a linear color space, but what we're viewing is a viewer LUT on top of that so we can see what the final result will look like when it's colored. A lot of the times with viewer color spaces, you'll run into clamping issues where you lose values because the colorist's goal isn't to retain data, it's to make the image look visually appealing. So now let's start talking about how this applies to Nuke. When working in Nuke, there are typically multiple color space conversions occurring, and it's important to know exactly what's going on. At the most basic level, there are 3 color space conversions happening. We have our read node input conversion, and the goal of this is to linearize our footage. We have our write node output conversion, which is going to return our footage to its original color space. And then we have our viewer conversion, and this is the LUT on top of our linear color space so we can view it in an aesthetically pleasing manner. So let's hop into Nuke and see this in action. And so I've brought week 2's footage into Nuke to use as an example. So what I want to do first is turn off all the color space conversions that Nuke is currently doing, because there's 2. We have an input conversion, which is converting it from Alexa, and we have a viewer conversion, which is up here in our viewer as sRGB. So to turn our input conversion off, we can set this to linear, which means I want no color space change to happen. And in our viewer, we can set our color space to none. Now what we have is a washed out log image, because that's what this was shot in. If you were to open this in any other program, this is what the color would look like, nice and flat and washed out. And so let's explicitly do an input color conversion, not using this color space tab. I'm going to make a color space node. And you'll see we have our familiar list of color space options here. And ignore this D65 and sRGB. Really, you don't need any of these knobs except for the in and out tab right here. And so if you look at this dropdown, these are all of Nuke's default color space conversions. This list is the exact same as the list we have in our read node. And you'll notice the list is the same in our in and out pipes. And now what I'm about to tell you is the most important concept to grasp about color space in Nuke. Each color space option has two distinct curves to it. It has an input curve and an output curve. So if we set Alexa to our in, we're using our input Alexa curve. Let's change that back to linear. If we're setting to out, we're using our output Alexa curve. And you can see two very different things happened to our footage. Let's look at a quick graph of what this looks like on a curve. As you can see on the input conversion on our left, it's the perfect opposite of the output conversion on our right. And so if you were to apply both of these to your image, the result would be no color shift. And so where we want to work in Nuke is right in the middle. This is our linear color space. So now let's go back into Nuke. I have my color space node here. I'm going to change this back to linear. And I'm going to set our input to Alexa. Let's copy and paste, and I'll have a duplicate here. And I will change this color space to Alexa as well, because the read node color space tab is looking for the input curve of the selected color space. And so if we A/B between these two, you'll see there's absolutely no difference because the same exact color space curve is being applied. Converting your color space like this is pretty unorthodox, but it's still technically correct. You could read all your footage in as linear and use color space nodes to do explicit transformations. So what exactly is happening when we're using our input color space conversion? The simplest explanation is that we're expecting a color space that has a known curve, and we're telling Nuke to multiply our footage with that inverted curve to give us a linear result. That's why selecting the right color space is important, because it'll give you the most accurate linearization possible. Now let's take a look at the output variant of our color space here. So if we were to make another color space node for the sake of keeping this nice and organized, we'll just call this our input conversion. Now, if we wanted to delinearize our footage, we would use the output flavor of the Alexa curve. And you'll see when we turn these off, there is zero shift that happens in our footage. I'll just label this output conversion very quickly. And so this output conversion is what happens when you use a write node. When you decide to write this out and you select a color space, it's using the output flavor of your color space curve. It's tricky when you're looking at this in Nuke because you can't actually see the color space conversion that happens. It's occurring on export. But this is the best way to visualize it with the color space node. If you'd like, you could copy this output conversion, throw it here. Again, this is delinearizing our image, make a write node, and write it out in linear. Again, linear means there's going to be no color space transformation happen. So when you write this out, what we're seeing in Nuke is exactly what we will get. And so I'm going to delete this really quick. And now maybe it makes a little more sense why the general rule of thumb is to have your read node input color space match your write node output color space, because they're going to cancel each other out and not color shift your footage. Now that we understand how our input and output conversions are happening, let's take a look at the final conversion that Nuke typically will be doing, and that's our viewer color space conversion. So we bring in our nuke footage and we linearize it like this. It doesn't look good, but this is technically correct. If we look, this lamp is reaching at 17, which is exactly what we want. And you can see that nice little fall off of the light because it's saying this left side is 16 times brighter, actually even more than that, than this near right side. And that kind of luminance disparity is exactly what you're looking for. If we didn't do a color conversion on this, look, this is reading around 0.87 and the right side is at 0.24. And that is not even remotely close to the actual brightness difference on the left and right side of this potted plant. So we have our image in the right color space. And by default, Nuke applies a viewer conversion, and that is sRGB. We talked a little bit about how Nuke's standard sRGB conversion isn't as good as Ace's, but for the sake of this example, it's fine because this image doesn't look too bad minus the highlights. And so what this color space is doing is it's taking the output curve of the selected color space and applying it on our viewer only. And you can see it's not actually changing the values. Let's go ahead and sample on this bulb and we can see how bright this is. When we change our color space for our viewer, you'll notice that our RGB values are not changing. And that's because this viewer is a post process. It's not actually affecting our pixels under the hood. It's just giving us something a little more visually pleasing to look at. And ideally, you want this viewer process to match your final color environment as closely as possible. And so we can mimic what is going on in our viewer process here. We'll set this to none and turn it off. We'll make another color space node. We'll look at it. And if we set our out to sRGB, this is the exact same thing as setting our viewer to sRGB. It's using the output curve when you have a color space option up here. Let's take another look at this, but we'll use Aces this time. So we can go ahead and change our settings to Aces. We're all errored out. We can set our viewer color space to raw. Raw is Ace's way of saying don't do any color space conversions. And we will set our image here to Ace's CG, which is the same thing as linear. And we'll see this looks exactly the same as when we had it in Nuke's default color space. And now we need to use Ace's flavor of color space transformation nodes, which are OCIO color space. And so again, to make this an Alexa color space, we'll change it to Airy EI800. And now this is linearized. And now we can go to our output flavor, look at sRGB, and there's our viewer color space. You can flip through these to see which of them you think looks nice. I like Rec 709 and sRGB typically. And then we'll change it to raw again. Let's make another OCIO node. Now, if we want to mimic our viewer color space, we can grab any of these output curves and apply them. And then this is exactly what we were seeing in our viewer. And there's something I would like to make very clear. Even though this category of color spaces is called output, each of these color spaces has a distinct input and output curve. This naming convention, I think, is a little more confusing than it needs to be, but just keep that in mind that there's really two curves for these output color spaces. Now back to talking about our viewer process. The disadvantage of creating our viewer process this way is that as we're sampling, this actually does change the relative values. Let's go ahead and sample in this area again. It's reading at 0.99. When we turn this off, it's back up to 17. When I put this to Rec 709 in our viewer, it doesn't move. And so that's why you don't generally work like this. And remember, we made that viewer process in weeks 1 and 2. Let's go ahead and do that really quick. With a color space node, we'll go to our viewer settings. If you can't reach your viewer settings, just make sure you clear out all of your properties, then hit S in the viewer. We will copy the name, paste it here. Oops, that didn't copy and paste very well. We'll copy, paste the name, and now we have our viewer process. So we can change this to Rec 709. We'll turn this one off, and you'll see this also does not change the value because it's a post process that is happening. So you can make all the viewer color space adjustments you want, but your underlying values from using these two will not change. So I'm going to delete this and keep this as sRGB. Actually, let's change this to raw. I want to talk about something that upsets me greatly, and that is the vector field node. When I was learning how to apply color space, this node really threw me through a loop, because you would think color space in would be applying an input curve and the out would be applying an output curve, but it's actually the exact opposite. I'm going to go back to standard Nuke color space for this. Go back to linear. So we'll pipe our vector field in here. We'll grab our LUT from week 2. And this looks correct. This is what we would expect it to look like. So let's start doing some color space adjustments like we would be doing if we were compositing. So the input curve is Alexa, and now we have our linearized footage. Now in our vector field, this will not be applied correctly because it's expecting a linear input. So you can actually use this color space in to apply the output flavor of our Alexa in here so that it looks correct. So despite being named the same thing, the color space in tab in your vector field does the opposite of the in tab in the color space node. The color space in knob in vector field will apply an output curve, where the color space out tab in the vector field will apply an input curve. So if we were to change this to sRGB, now we have an sRGB input LUT applied. And remember, our viewer applies an output LUT. So if we change this to sRGB, they cancel each other out and give us our desired result. This looks exactly as we would expect it to with our LUT. This is very confusing, and it just really bothers me that it's not more explicit. It makes sense if you're looking at just the vector field node, but when you look at it in the context of Nuke, naming it the exact same thing as another knob but having it do the opposite really doesn't make any sense to me. And that'll be the end of my vector field color space rant. And so now that we know how exactly color space works in Nuke, let's talk about how we select color spaces. Your ability to pick an accurate color space is entirely dependent on what you know about your footage. We're going to go over the 4 questions I ask when I'm trying to determine a color space to use. First, is there any metadata that explicitly says what color space or gamma curve was used on the footage? 2, do we have any set reports or written documentation on what color space was used for your camera? 3, do we know at least what brand of camera this was shot on? This will limit our search to color space curves specific to that camera. And then if you don't know any of the above, you need to identify the current category of color space that it is in and do your best to approximate. If you don't know any of this information, it can be very difficult and potentially impossible to discover the correct color space. A lot of footage that has been color corrected, it really is impossible to properly linearize it. And that's one of the reasons that stock footage can be very difficult to linearize, because there's not really any way of knowing how the color has been manipulated. Now let's see this in action and talk about the color space that I shot for this class and how I selected that. Footage for the first 4 weeks of this class was shot with a Blackmagic cinema camera. This camera has its own flavor of a log curve. It uses Blackmagic log, and Aces really only has high-end cinema cameras to choose input curves from. So what do? Well, you need to find a curve that closely approximates the one that you're using. In this instance, the Blackmagic log curve is very similar to the Arri Alexa log CV3 curve. And so I ended up using that to get the most accurate linearization possible within ACES. It's definitely not a perfect one-to-one match, but I know that it is very close to an Alexa, and it's definitely within the same category of log, and so it was good and okay to use. Let's talk about another type of camera that's commonly used that it may be a little tricky to find the color space for. And I'm talking about DSLRs. DSLRs, modern ones do have some log curves, but a lot of them don't. They just shoot standard Rec 709. There's different hacks for DSLRs to get curves, but it can be very difficult to figure out what exactly you should be using. If you're using the default curve from your DSLR, odds are it's an sRGB or Rec 709, and that's how you should interpret its color space. The trick with the sRGB Gamma 1.8, all of these kind of viewer color spaces, is they typically don't linearize very well, and they don't give you a large range of luminance values to play with. And that's just a casualty of working with a lower end camera. And unfortunately, this goes for a lot of stock footage as well. Anything that you get that looks visually appealing, that it's been color corrected to look good, you'll probably have to use one of these viewer color spaces to transform it. And that's why the general rule is if you don't know the color space and it's been color corrected, use sRGB. That's why in week 2, we used sRGB for that stock photograph that we used. And in week 3, for the stock video we used, that was also sRGB because there really wasn't any way to tell what camera it was, but it looked like it had been colored and edited. So we used a viewer conversion. Now, when you're using CG elements as EXRs, like we said earlier, they will almost always be linear 99.99999% of the time. They're going to be linear. And that's a pretty good rule of thumb for EXRs. If you don't know what color space they should be, it's probably linear. And now is where I do have to make a confession. In week 1, we should not have used the sRGB color space. That technically was not linearizing our color. I did this mainly because we were just getting started in Nuke, and I didn't want to even begin to dip my toe into color space because of its complexity and how abstract it is. I wanted us to get compositing, and if we would have had it in Alexa v3 log C, we would have had to play with our color because sRGB viewer color space doesn't show the highlights very well. There are a lot of reasons that I didn't want to use it since we were just getting started. And since we weren't really affecting the color and brightness too much in that image, I felt that it was okay to cheat. But if we were starting that shot now with the knowledge we have, we would have read it in as Alexa, most likely in ACES, and then viewed it with ACES sRGB or ACES Rec 709. And now that I have that off of my chest, I just want to recap why we use color space. I know that was a lot of information. I think this is the hardest abstract concept to understand in Nuke. And it is important because it will bring our object into the real world in terms of brightness. And it's going to unify all of our elements and how they react to changes in brightness. You know you've messed up your color space when you increase your gain by 0.1 and then suddenly your sun is 20 times brighter than it originally was. That may seem like an over-exaggeration, but I've seen it happen, and it's why color space is so important. So we're at the end. Thank you very much for sticking with me through this very long theory video, and I'll catch you guys in the next one.